Hello my dear student, today I am going to talk about existence and the uniqueness theorem in differential equation. Because in continuous dynamical system we are going to use differential equation and solution of differential equation. So it is very much important to understand the existence and the uniqueness theorem of differential equation. Okay, let us briefly see what do you mean by existence and uniqueness theorem of this one, ordinary differential equation. In fact, it is initial value problem of differential equation. Okay, so initial value problem. Okay, so let us see let us consider there are two conditions to ensure existence and a uniqueness. Number one is existence. The solution may exist passing through a point. The solution may exist passing through a point. Through that there may not be any solution. Okay, so if the condition fulfilled, then there will be definitely some solution passing through that point. Another one is if there exists some solution, whether the solution is unique or not. Okay, so that is the two things in the ordinary differential equation, initial value problem. First, let us see this example, dy by dx. Okay, so dy by dx, or first order differential equation, dy by dx, we can write the right hand side as a function of x and y. Okay, so it is all about this function, property of this function. So suppose let us take an arbitrary point AB. Let us take an arbitrary point AB. Through this point, is there a solution of this differential equation? Okay, and how many such solutions are there? So that is the thing. So if the function, if this function is continuous in an open neighborhood of this point, what is this point? This point means if y is a solution, y of a is equal to b. Okay, so if this function is continuous in an open neighborhood of this point AB, then this theorem says that there will be solution passing through this point. There will be definitely solution of the differential equation. Okay, solution of this differential equation passing through this point. This is about existence. Okay, if the function in the right hand side of the differential equation is continuous about a point AB, then passing through that point AB there will be a solution of the differential equation. Then the second condition says that how many such solutions are there. Suppose then you find out the partial derivative, del f by del y. If this partial derivative is also continuous at this point AB, in another language this is called Lipschitz condition. Okay, Lipschitz condition. Now let us use this partial derivative condition. If this partial derivative is continuous about this point AB, okay, then so the solution is unique. That means what? If these two conditions are fulfilled, there exists one and only one solution passing through this point AB. That means there exists one and only one solution y such that y of a is equal to b. So this is called initial value problem. Okay, so the solution to the initial value problem exists and is unique if these two conditions, if they are fulfilled. If these two conditions are not fulfilled, then the theorem doesn't say anything. Okay, you have to be very careful about this thing. The theorem says that if these two conditions are fulfilled, there exists one and only one solution passing through this point AB. Okay, if theorem doesn't fulfill, if the differential equation doesn't fulfill these two conditions, nothing is mentioned about the existence and the uniqueness. There may be some solution, there may be many solution, there may be unique solution. All type of things can happen in that situation. Okay, what I mean, if the differential equation, given differential equation, doesn't fulfill these two conditions, okay, that means the function f of xy may not be continuous at this point a b. Okay, then there may be solution passing through this point, there may not be solution passing through this point also. So we cannot say anything about the solution. Okay, so again, if the partial derivative is not continuous at this point, okay, so there may be many solution, there may not be any solution, or there may be infinitely many solution, okay, or there may be two solutions, something like that. So nothing is mentioned about when the given differential equation fail this condition. Okay, the theorem says that if the given differential equation fulfill these two conditions, then there exists one and only one solution passing through the point a b. Okay, so this is about the existence and the uniqueness theorem of the ordinary differential equation, because in continuous dynamical system we are going to talk about differential equation, its solution, and lots of other properties like fixed point, phase curve, all these things. Okay, so we have to understand the existence and the uniqueness theorem of differential equation. Okay, so that is about the theorem, existence and the uniqueness of initial value problem of the ordinary differential equation. Let me remind again, there are two conditions. If the given differential equation, initial value problem, satisfy these two conditions, what does the theorem say? The theorem says that there exists one and only one solution passing through that point a b. Okay, if the given differential equation, initial value problem, doesn't satisfy, okay, both a condition or one of the condition, it satisfies one condition but it doesn't satisfy another condition, then okay, the theorem doesn't say anything. There may be solution, there may be two solution, okay, there may be infinitely many solution, there may be unique solution also, okay, there may not be any solution also. So that is the thing. If the theorem doesn't satisfy these two conditions, it doesn't say anything. We are in dark, we don't know anything. Okay, we know nothing about that. You have to actually, you have to actually solve it and check it. Okay, we are in dark. All right, but if the given differential equation, initial value problem, satisfies these two conditions, then we are 100% sure that there exists one and only one solution passing through the point a b. Okay, this is about existence and the uniqueness theorem of differential equation. All right, so let us see some example. So first, dy by dx is equal to minus of x divided by y. Let us see, randomly you take 1 point, 3, 2. That means when x is equal to 3, y is equal to 2. All right, so what is the function in the right hand side? You have to see the function in the right hand side. What is the function in the right hand side? The function is minus x divided by y. So this function is continuous if y is not equal to 0. At every point when y is not equal to 0, this function is continuous. When y is equal to 0, it is something divided by 0 that is undefined. The function is not continuous. Okay, so therefore this function is continuous. So when y is not equal to 0, say here y is equal to 2. All right, y is equal to 2, so y is not equal to 0, so this function is continuous in an open neighborhood of this point 3, 2. All right, again let us evaluate the partial derivative of the function. The partial derivative is x divided by y square. It is also continuous if y is not equal to 0. When y is equal to 0, this function is not continuous. This partial derivative is not continuous. So therefore, since y is equal to 2, this is also continuous. Okay, so both the condition fulfill. So what does the theorem says? That there exists only one solution. Solution must be there, and must not be two there should not be any two solution also. So there exists one and only one solution satisfying this condition, initial value. That means what is the condition? Suppose if y is the solution, y is equal to pi x is the solution, okay, then y at the point 3 is equal to 2. All right, so there should be one and only one solution. Let us verify. Verification. Let us verify this one. So the given differential equation, you can separate the variable easily. After separation of variable, you can integrate like this, okay. This is separation of variable, and this is the constant of integration, okay. So then you put, if you have to find out the constant of integration, you put the value 3 and 2 here. So it is constant of integration is how much? 13 divided by 2. This is the constant of integration, okay. So then, you know, after simplification, what you have is y square, sorry, this is not, you know, this is bracket. Y square is equal to this one, 13 minus x square, okay. So if you take square root, you will get here plus minus this one. So in fact, you have two functions. One is this one, another one is this one. You know, another one is square root of a real number cannot be negative, okay. Square root of a real number cannot be negative. So when you put x is equal to 3, you are going to get y is equal to 2. But here negative is here, so this doesn't fulfill the given condition. Although this satisfies the given differential equation, but it doesn't fulfill the given initial value, you know, condition, initial condition. This is the only solution, okay. So how many solutions are there? There is only one solution, okay, satisfying that given initial condition. So it verifies, okay, verification, okay. So the theorem is now, in this case, it is okay. Now let us see again, when y is equal to 0, what happened? Let us see. You know, when y is equal to 0, that means x is equal to 4. You take any point x and y is equal to 0. The same differential equation, let us see. So here the function f of xy is equal to minus x divided by y is not continuous at this point. When y is equal to 0, this is not continuous. So we don't know anything about existence of the solution. Is there a solution, or is there two solutions? We don't know anything about. Passing through this point, we don't know anything about the solution, okay, because it fails the first condition. This function is not continuous at this point. Therefore, we cannot say anything about the existence of the solution. There may be solution, there may not be solution, okay. Again, let us see. The partial derivative here is x divided by y square. This one is also not continuous, okay, because when y is equal to 0, this function is undefined. So it is not continuous at the point 4, 0. Okay, it is not continuous. All right. So here also we cannot say anything about the uniqueness. Okay, there may be solution, there may not be solution, there may be more than one solution. Okay, we cannot say anything about it. But let us actually see what does it happen. Anything can happen in this situation. There may be solution, there may not be solution, there may be unique solution. Okay, so let us see by integrating, you know, again the same differential equation. After integration, you will get what? Y square plus x square is equal to c. So when you put x is equal to 0, y is equal to 4, what do you get? C is equal to 16. Okay, you get c is equal to 16. You know, then y square, this is equal to 0. So these are two solutions. In fact, these are two solutions. These are two solutions of the given differential equation. Let us check whether these two solutions satisfies the initial condition. So when x is equal to 4, this is 0, plus 0 is 0. Here also, when x is equal to 4, this is 0, minus 0 is also 0. Okay, so these two solutions satisfy the same initial condition. So there are two solutions. Okay, solution is there, but it is not unique. All right, solution is there, but it is not unique. So see, when the condition fail, there may be solution but may not be unique. All right, so this is the case. This is the case. Okay, so there are two solutions in this situation. All right, so next, another let us see another example. Suppose this differential equation, dy by dx is equal to y upon x at any point a b. Let us see, suppose a is not equal to 0. When a is not equal to 0, let us see, the given differential equation is dy by dx is equal to y by x. So the right hand side function f of xy is equal to y upon x. Okay, the right hand side function is y upon x. So this function is continuous at every point except when x is equal to 0. So since the point a is not equal to 0, this is going to be okay, né? The function is continuous. All right, this is continuous whenever a is not equal to 0 or a is not equal to 0. All right, again, what does it say? It says existence of the solution. There may be 2 solutions, 3 solutions, but there should be at least one solution passing through this point. Okay, it says this condition fulfilled, says that. Okay, next let us see the partial derivative part. This is also del f by del y is equal to 1 upon x. This function is also continuous when a is not equal to 0. Okay, so when a is not equal to 0, condition 1 and condition 2 are fulfilled. But what does it say? It says that there exists a unique solution passing through this point AB. Okay, there exists a unique solution passing through this point whenever a is not equal to 0. All right, so that is okay. Yeah, so what is the nature of the solution? Y is equal to b by x. Okay, y is equal to b by x. So what does it represent? It represents a family of straight line whose slope is b by a. All right, so if you take different b and a, you will get different straight line passing through the origin. Okay, passing through the origin. So whenever a is not equal to 0, so this one, you make this one is a slope, and then you draw a line passing through the origin. That is going to be a solution from this one. And next is, now let us see, when a is equal to 0 but b is not equal to 0, what does it say? When a is equal to 0 but b is not equal to 0. Okay, that in that situation, let us see, dy by dx is equal to y by x, and this is your right hand side function f of xy. So when x is equal to 0 or a is equal to 0, this is not continuous. Okay, this is not continuous. Something divided by 0 is undefined mathematics, so it is not continuous. So for those points when a is equal to 0, the function is not okay. The function is not continuous. Okay, and let us see the second condition, del f by del x. Del f by del x is y upon x. Here also, when a is equal to 0, for those points such that a is equal to 0. Okay, so the partial derivative is also not continuous. Okay, so what does it say? It says that it says nothing about the existence and uniqueness. There may be solution, there may not be solution passing through that point. Okay, there may be infinite solution. Okay, let us see in this case what happened. So let us see, in fact there is no solution in this situation. There is no solution in this situation. Okay, in this situation, in the earlier case there was solution, but here there is no solution. Okay, so case number 3, when a is equal to 0 and b is equal to 0, what does it say? When a is equal to 0, this is not, it is not continuous. The denominator is going to be 0, and partial derivative is also not continuous. Okay, so 2 conditions fail in this situation also. So what is the conclusion? Here there is no solution. Let us draw some diagram for the last cases all together. Let us draw some diagram here. See, let me draw some diagram here. This is your x-axis, y-axis. This is your x-axis. Okay, suppose the point a b is here. A is not equal to 0. Okay, and b also not equal to 0 here. So then, so b divided by a is going to be your slope of the straight line, b divided by a. So then this line, this line, let me draw. This is straight line. I may not be very good in the, so this line is going to be a solution. Suppose AB is here, CD, let us see, CD is here, CD is here, then you'll draw a line passing through this CD and passing through the origin. This is going to be a solution also. Suppose, and then when A is not equal to 0 but B is equal to 0, now what is the line? Line is x-axis. Line is x-axis. What is the represent? Y is equal to 0 is the x-axis, na? Y is equal to 0 is the x-axis. So this is going to be a solution. This x-axis is also going to be a solution. Okay, here also if you take one point here also, passing through that point you draw one straight line, that is going to be solution of the differential equation. So unique solution is there. Only one line passed through this one, so unique solution is there in that cases. First case, when A is not equal to 0. Okay, when A is not equal to 0, you have a unique solution. When A is equal to 0 but B is not equal to 0, this is the case. This is the case. Okay, this line, so this is not going to be y axis. This is your y axis. All right, this is your y axis. So if you take any point on the y axis, there is no solution. All right, there is no solution. You take any point in the y, there is no solution. What is y axis? Y axis means x is equal to 0, but y, you don't know y. So that function, if you don't know, you cannot differentiate it. The differentiation, derivative dy by dx is equal to, that is y by x, na? That equation should fulfill by the equation x is equal to 0, na? But this is not going to be, a solution. So there is no solution. And the theorem also says that what? Partial derivative is not continuous. The function is also not continuous at this point, na? So the two conditions are not fulfilled and there is no solution, right? But we saw that in the origin also, when A is equal to 0 and B is equal to 0, here so many curves are here also this is also solution. Okay, so in the origin the first condition is not fulfilled. In the origin the second condition is also not fulfilled, but you have infinitely many solutions. This is also solution passing through origin, this is also solution passing through origin, and this one is also solution passing through the origin. Okay, see, when the two conditions are not fulfilled, anything can happen. I told you here also the two conditions are not satisfied, but there is no solution. But here also the two conditions are not satisfied, but there are infinitely many solutions. All right, there are infinitely many solutions. In some earlier cases there are two solutions also. Okay, so this is some brief brief introduction of the theorem of existence and the uniqueness theorem in differential equation initial value problem that is going to be used in our study. So I want to give this much today. Next class will be uploaded next day.